And we'll just. I'll just minimize this. So, hang on. So here's the actual code. I don't know if it is visible to you. If not, let me see. Can I actually pinch zoom here? Can I control plus here? Yeah, I can zoom in into the actual. There we go. And I'll just backspace. There we go. So let's talk about the code a little bit. I'm just gonna go through it. I've already uploaded it for those who actually wants to check. Again, this is one of the ways, as I already have mentioned. I didn't create a complete project. I just simply I made a code snippet, and I run it immediately within MS like Visual Studio Code. And I think I already showed you like in the first class of programming how to programming 3 how to do that. Feel free to revert to the first class and check it out. So what's happening here is, and you should be having this in the material, this code snippet actually, but it's actually different. This one, I think the one which I pasted is you can run it in Visual Studio. So if you create a new Visual Studio project, you just simply and make a console application and just paste the code directly, it will work. So what's happening here is, in order for me to test the balanced brackets bit, I need to know actually what is the what is the opening bracket and what is the closing bracket for it. So for example, I would like to know that, for example, when I look at the bracket, is this, for example, opening and this is the closing of it, for example, right? So this is the way that I can say, yeah, this is the opening and this is the closing bracket of the same type, right? So this is matching pair is the one which I actually, what it actually does, it does that actually for me. Check is balanced. Let me minimize this again. So I'm actually looping over. So I have actually a stack of characters, and then I'm actually looping over the actual string. Now, if you loop over strings, at least in C#, a string is an array of characters, and you can actually loop over it. You can just simply say for I equals 0 and I less than whatever that string. So this string dot length, and then you get actually the length of the characters, and you can index through it, and every time you index through it, you get an actual character. And I think it's probably similar to C++ to a certain extent. And then if I see an opening bracket, I'll just simply push it into the stack. And if I see a closing one, and I have an empty stack, that means it's not balanced, right? However, if I actually see, if I actually check a matching pair, right? So if they are not matching, that means that something is wrong when I'm actually popping in from the stack, because whatever is actually open first has to be closed. Has to be closed last at the end, right? So if I actually open a bracket here. Right, so probably I need to zoom out just a tiny bit. Hang on, so I can actually have the full code in Spectrum, and hopefully you guys can see all of this. You can see this, right? You can actually write to me in the chat. How good is visible is this?
Yeah, it's good.
Okay.
The whole code.
Okay, perfect. So I mean, the main thing is readable through the stream. That's what I want to get to. So if you open a bracket, and then you open it, and then you close one. So we have actually opened the last one which has been opened has to be closed first. So the last one was actually the round bracket here, or the braces rather, and then we need to close it first. So if I actually see something that is like, when I'm actually closing right now the bracket, if I actually find another type other than this one, then it will actually return a false, and it will say, hey, this is unbalanced. If it actually goes through the whole loop, without any problems, and we have an empty stack, then it actually should return true, right? So here I'm returning if the bracket stack.count equals to 0. So in this case, if I actually, if this actually runs, let me try to, for real. There we go. I can actually hit run all, and it's actually balanced. So you see here, here's the output in the bottom. But if I actually like add, oh, come on, really now? No keyboard? There we go. So right here, if I actually just simply add one more, for instance, and right now, if I actually run all, it will give me actually not balanced, as you can see in the bottom here. Okay, so so this is actually the thing which I actually wanted to show you the last time. You have already the code uploaded. You already have it all in the materials, so you can just simply check it out. You can expand upon it and do whatever you want. Now that's actually done. I can actually close this or just simply open this. And let's actually talk about queues. Today we're going to cover queues and algorithm analysis. So let's actually talk about queues first before sorry, before talking about algorithmic analysis. So and then queues are actually quite simple. They are actually similar to stacks, except they are actually first in, whoever actually first come, first serve, or first in, first out, instead of last in, first out. So it's a FIFO instead of a LIFO, right? So like stacks, queues are lists with protocols or with a protocol. Okay, you can call it a protocol, you can call it a policy, you can call it a constraint. Okay, so that's this is a forward slash. So it's actually a fancy kind of a list where insertion is done at one end and removal or deletion is performed from another end. Okay, so a queue, the policy, basically, we can actually let me color code this. So the policy is first in, first out. Okay, which is so this, which is FIFO. Okay, as opposing to stack, which is LIFO. Okay, so this is what queues are all about. So if we actually have a look at a queue in general as an ADT or as an abstract data type, here are the functionalities, or here are the following operations. So let me just get this like so. So Q, hang on. As ADT. So Q as an ADT has the following operation. It has insertion. In the Q lingo, it's called InQ. Okay. And people actually, they say InQ in C# when you have a Q object or a Q data structure created. So you say var something equals to new Q. When you say something dot, it will say InQ or DQ and so on and so forth. Okay. So insertion is InQ. And when people will talk to you about the Q, they will say either add to the Q or they say InQ. You're gonna get both of them. But majority of people say, I think they say InQ in general. So deletion, this is also another functionality, which is DQ. DQ. You have another one, which is peak. So this is DQ on steroids, meaning that get return the element. Why did I? Hang on. Return the element without removing it. Okay. So this is peak. It exists in many implementations, at least in the C# implementation, it exists. And you have the same like in stack. It says check if empty. Okay. So if you'd like to say, you know, like check if a queue is empty or not, it should actually provide that. So if anybody using a linked list or using an array implementation, using whatever implementation they have in mind, if they implement these stuff as you see here using that policy, okay, that means that you are having an actual queue, regardless of what you have used. Did you use a multiple chips to implement that without any, like if you implemented that with some transistors or you implemented that through code, nobody cares. As long as you satisfied the policies and you implemented these functionalities, maybe you can drop the peak if you want to, then you actually have a queue in your hands, right? So you successfully implemented the queue. All right, so let's actually look at a quick example here. So if you actually would like to in-queue something, so let's say here's an operation. You say in-queue in-queue 10, for example, in an array. Right? So in-queue 10. So you actually like pushing it from here, for example. Okay. And then you say in queue 9, so your queue will look like something similar to this. So this is 10, this is 9. So I mean, this is like a visualization. It doesn't necessarily mean that, I mean, it doesn't necessarily mean that you are actually inserting from this direction literally in code. This is just a presentation, nothing more. And then you, for example, also, let's say in Q8, because I mean, if you add actually into the list, in fact, so i.e. in Q, so if you actually add into a list, you will be adding to the list the same way. However, when you dequeue, so let's say right now we're going to dequeue. Okay. And you should say nothing here because you are just simply removing from the queue1 element. It will actually return to you the element. So it will kick out 10 from the collection. So here's so it will be like, it will kick out 10 and it will give it to you in a variable. So you hold it in a variable. And then you have 9, and then you have 8, and then the empty spaces. If you try to dequeue again, then you will be, so let me just simply like, it kicked out the 10 here. So if you will be having something like this, 8, and then the rest of the, the rest of the array. So it will just simply give you 9 here, okay? Now, obviously you can say, hey, what about this piece of memory? You actually don't care that much because you don't think about defragmenting the memory and make things happening correctly. I mean, not happening correctly, but you don't care about like how many empty spaces you have in an array, because anyway, that array is being reserved as a block, right? You can actually start defragmenting things by, you can say, aha, okay, I'm gonna shift all the numbers. However, the problem with shifting is that if you have 1,000 elements and you dequeue one element, you have to shift 999 elements forward, which is completely inefficient. So you will not actually, you might want to do that at a certain point in time, but this is stuff you are like, you care about. You care about this in some other edge cases, which probably I don't know if you will ever meet, but you don't actually be afraid about like, or don't be worried about, for example, having empty spaces like these. So for those who actually might be thinking about this. So so let's actually talk about the use cases. Oh, by the way, any questions so far?
No.
Okay. Okay. All right. So can anybody give me a guess what you would be using a queue for? I mean, with the last class with the regular students, I had very interesting examples, to say the least. I cannot remember them right now all, but I had actually pretty interesting insights on what people see that they can actually use as a queue. So I'm actually curious to see what you guys have in mind. Feel free to write in the chat. Any guesses? Okay. Since everybody ignores me, organize shared resources for task execution. Such as, for example, just write it here, printing jobs. Or processes in your printing jobs over a network. Or processes over on a PC, for example, right? So in a printing jobs, imagine the following: like you are on a network, and we are sending, for example, I am at the faculty, and all of us sharing the same printer, and I actually like send a document to be printed, and a colleague of mine sends another document to be printed, right? Imagine that I'm sending 10 pages of mine, he's sending or she's sending 5 pages of hers, and another one is sending another 7 pages. Imagine that all of them, they suddenly, like the printer just simply says, aha, okay, I have a bunch of papers to print. And then it simply like prints one page for me, and then the next page comes out because of one guy sent a couple milliseconds after me, like, aha, okay, let me print that page. And then another guy sends another page, like when he sent another job, then another page. And then you get like all the jobs are being mixed up into a big gigantic mess, because you have a couple of pages from one person, another couple of pages from another person, and so on and so forth. So in printing jobs, what happens is on the printer itself, there is a sort of queue in there where you have a printing job queue. So it says, aha, okay, this guy came first. He asked to print something. I will print his papers first, and I will keep everybody else on the waiting list. So they will actually, like, the printer will actually say, okay, I will take this, and I'll start printing out all the papers for the person one, and then person two comes in and says, okay, here's his job, or her job, and let me actually print this out. So it's actually quite an interesting, I mean, it's actually quite valid example, and it's very straightforward example on how to use queues. You can actually organize a process execution, but we are not covering this version of it yet. Maybe actually when we get to, I think, heap, you will see it. Organizing process execution, which is an application for priority queue. So imagine that you are on your PC. This is also one more thing: customer support calls. So if you are actually having a waiting, you are calling a call center, and then you have an answer machine which puts you on a queue, and first come first serves kind of thing. So that's one thing. So for example, regarding this, if you are on your PC, when you can actually, in the task manager, you can easily set the priority of a certain task, and you say, hey, this has the highest priority, and nobody can interrupt this, or the CPU should take care of this. So the operating system will prioritize that task. Other than that, your PC is actually prioritizing your processes based on these priorities. And sometimes, because you have, for example, at least in the old days when we had a single core CPU, we had like the CPU has to make a dance in the old days between all the processes, like a round robin dance, and then it executes this task a little bit, and then it executes the other task a little bit. Maybe it can actually skip another task due to the higher priority. So for example, it says, okay, this guy is launching, I don't know, a very important process in the operating system, which needs to keep the operating system stable. So it will actually give this more resources than the others. So probably your other software will start to get slower. But again, this stuff you don't see it right now, because actually CPUs have become more modern, and they solve these problems quite quicker. Another interesting implementation which I would like to mention here, and I will leave it for your research, is called let me actually write it down here. Another interesting implementation of queues are circular queues, or sometimes some people refer to it as ring buffers. Sometimes referred to as ring buffer. And it's just a simple piece of memory where you actually set up. Usually people present it like this in books, like a donut. And then you have elements in here, right? And let's say for a second that this is the head, right? And you insert from here. So in queue here, and then you in queue again, and then you in queue again, and so on. And then all of a sudden you start to dequeue. So 10 will be removed, so you don't have 10. And then you dequeue, for example, 20, but then you in queue, let's say 50, so it will be in queued here. Then you in queue 60, 70, 80, and then you dequeue, for example, 30, so 30 goes out. So you will take this out. When you say dequeue, you don't specify what you are dequeuing. You just simply say dequeue and it will dequeue out. And then you say 90, and as you can see here, I don't run out of space. I just simply go on. And then 100, 110 if I'm in queuing again. And it depends on the implementation. Sometimes some people will say, if I would like to in queue 120, it will just simply override this to 120. Some other people might give another implementation where it says the ring buffer is full, and I cannot actually allow you to write anymore. So so yeah, this is one of the interesting implementation of queues, like a ring buffer. So that's actually everything about the about the queues. Right there, I'll just pull a complete line, and we move on to the next topic. Do you have any questions regarding the queues?
No questions.
Okay. I think Adil already has
Sorry,
covered it
Professor.
with you. Yeah?
I wasn't on the last presentation, and you mentioned some research. Can you repeat what do we need to do the research for?
So I'm actually trying to remember, what did I say that you guys have to research last time?
You just mentioned the queues. You said I will leave it for your research. Do you mean some general research, or there is a mandatory research we need to do?
No, this is a general research, like the circular queue. I will leave it actually for your research. It's up to you. Like you can actually like look at it. It's not mandatory at all, but it's something that you might want to know about in the future, because the stuff which I'm mentioning here, there are many, not many, but there are some things where I say, okay, this is something that you guys research for. That means that maybe you will not see it on the exam, but you're surely going to see it outside. Like when you graduate or you're going to work in a job, people will actually talk about this. So it's good to know about this.
Okay.
All right, so let's talk about, now I'm actually going to leave the realm of data structures, and we will talk about the algorithm analysis. And this is actually super important that you understand how to analyze an algorithm and understanding the complexity theory. And I have to tell you, like, a lot of people get it wrong. A lot, and I'm not kidding. A lot, and a lot of them are professionals even. In fact, as far as I remember, here in Bosnia, there are all actually. I've seen a job posting where right now I think it's I cannot remember when exactly, but right now. Depending on the job, obviously, but I've seen people actually asking people that they understand this for work. So it's actually it's actually important tool in your hands to understand. If you're gonna be one of those people who are working with high performance computing or doing game development, then obviously you need to know this like the back of your hand. If you are gonna be a powerful engineer, you still need to know this. And if you don't encounter this as a junior, maybe surely you're going to encounter it in the future as a media or as a senior or a tech lead. So let's talk about algorithm analysis. So let me actually make it a little bit more dramatic by grabbing something like so. Algorithm analysis. This is super important to get and understand. First of all, just a side note, and I'm writing it here like a side note. We are, because you guys are in second year, we are learning asymptotic, sorry. Notations or asymptotic analysis. In this semester. Okay. Check out after the end of the series of these lectures about complexity analysis, because you need to understand this first before you move on. Check out amortized analysis. You don't need to check it out right now. You shouldn't. Check it out after the end of these lectures. Okay? Not this lecture. We have I think there are at least, beside this one, at least two more. So we can cover as much ground as possible. And then afterwards, hopefully you understand what asymptotic notations and asymptotic analysis is or are. And then you go on and then you can research amortized analysis on your own leisure time. Okay. So first of all, let's actually hammer down some certain details. What are the characteristics? What are the characteristics of an algorithm? What can you define? How can you say that this thing is an algorithm? If somebody comes to you and he says I made an algorithm, you and actually even if you come to somebody who's actually a senior or a lead in your team or somebody in your teammates, colleague of yours, and say, I made an algorithm, the first several questions or the several metrics you judge by that this is an algorithm or not are the following. So I'm going to actually write here characteristics of an algorithm. First of all, an algorithm first of all, before I actually finish the sentence, algorithms in general are steps describing steps to solve a certain problem. Okay, so that's it. That's what an algorithm by definition are or is. So an algorithm can take zero or more inputs. Okay, So that's the first thing, right? Now now somebody might be asking like, okay, if I would like to sort numbers, I need to give numbers as an input, and then I will get assorted numbers as an output, right? So what kind of an algorithm that doesn't take any input and gives me an output? Can somebody give me a guess?
Maybe we take something from memory. We don't take like inputs or numbers. We just take something from an address or something.
Yeah, but that's what you are saying is still an input, by the way. So you are taking something from memory and you input into your code or you input into the function in order for it to generate something else, right?
I was more referring to like a file stream or something like file.
No. This is still actually a file stream still considered as an input. Any other guesses? Actually, just to tell you also, like to give you to reiterate on that point, a file stream is like you are reading from the hard drive, right? You load the file into the memory, and then you need to operate on the data which is within that file. You will take that file take the data which you loaded from a file in the memory, and you'll push it into the function, which is whatever algorithm you have. So it's actually, that's why I'm saying it's considered as an input. But just to give an example, this is for example, a generative algorithms. You could simply, do you know like algorithms that generate worlds, that generate, so for example, Minecraft, you just simply like say play, and it will immediately generate for you a complete world. No Man's Sky, for example, you click, you generate a complete world, right? It takes 0 inputs and just gives you a completely crazy output, right? So this is one of them. One of why an algorithm could actually take 0 inputs. Okay, but an algorithm must generate at least one output, right? So that's actually super important. If you actually do not generate an output, that means that you are just simply taking in inputs or whatever, and then you run the software and then nothing happens. It doesn't spit out anything in the memory, it doesn't modify any values, it doesn't do anything. It just takes in stuff and it just doesn't do anything, right? So or just a piece of code that runs and doesn't do anything, or doesn't give something that I can use. So by that, you need to, in order for an algorithm to be an algorithm or useful, you need to generate at least one output. Give me something. Is this, for example, input is valid or not? So at least true or false, for example, you need to give. So that's one side of the story. Definiteness. Meaning must give a tangible, meaning useful also, a tangible answer. So do not give me something like, if I send something to an algorithm, it shouldn't give me null reference exceptions, or it shouldn't give me nulls, or square root of -i, or whatever, something crazy they give these days. But it has to, you cannot have an algorithm that doesn't solve a problem, practically speaking. It has to solve a problem, and it should give you an answer to the problem which you are giving it to. Finiteness. Meaning that you shouldn't have you shouldn't have an algorithm that infinitely loops without an output, which conforms to the previous point, right? That infinitely loops without an output. So that's one. Effectiveness. Means that it has to be effective such that it can be useful or used, right? And I will tell you immediately what I mean by that. To be has to be effective such that it can be useful or used. Okay, so these are the actual characteristics of an algorithm. If like imagine that you are trying to sort 100 numbers. So for example, when I say sort 100 numbers, you say, why would I sort 100 numbers? But when you think about it, say, okay, I would like to get all my employees and sort them by, and because I would like to give people who have the least salary a raise, please sort them by the salary in ascending order. So the smallest people with the smallest salaries, people with smallest salaries can get a raise of, let's say, 50%, but people with highest salary can get a raise of, let's say, 5% because they have already high salary. So you need to sort that. If you are actually trying to sort 100 employees and it takes you, I don't know, like an hour, that means it's not that effective anymore. It's actually kind of like, okay, in an hour, I could actually sort that 100 employee by hand right now, right? Now, obviously, I'm giving a very extreme example, but generally speaking, if we look at this from the other side, imagine that you are searching a product in Amazon, and imagine that you are waiting for that search result to return, and it returns like in 5 minutes. Right now, it's actually becoming a little bit more difficult to deal with. Right now, it's not effective searching algorithm, right? So, so effectiveness is one of the characteristics of a good algorithm, at least. All right. Now we can actually go into a break, and after the break, we're going to discuss how we are actually analyzing the algorithm. So we're going to talk about algorithm analysis. Okay. If you have any questions, feel free to say it live or voice, or write it in the chat, and I'll be happy to answer.
No questions for now. What's the duration of the break?
10 minutes.
Okay.
So I think it's like 1 and 13. If my clock is, or 1 and 12, if my clock is right. Can you hear me?
Yes.
Okay. So now the break is over. Let's actually get on with the analysis. So when we analyze an algorithm, we actually analyze it against several things here. One is actually time. How much time will it take to execute? Okay. Which is normal. You would like to know if the thing will actually run within a specific time frame. And it is actually super important to understand that that when you actually start developing, or when you're actually starting solving a certain business problem, where you would like to say, for instance, okay, my boss actually wants me to get a list of customers and do certain operations on them, whether calculate pensions or I don't know, raise salaries or whatever you would like to do, or you would like to do some analysis, some data analysis on the people, right? Data mining or whatever. And whatever algorithm you're going to use, you would like to make sure that it runs in a very plausible time frame. Now, one of the things which I usually tell people, like, it really depends on what kind of applications you are working on. Some applications, half a second of response time might be acceptable. In some applications, the half a second of a response time is completely unacceptable. So usually whenever actually you do analysis, you do that with profiling. So you need to profile your application before optimization. Do not optimize the application right while you are writing it. So always like see if you are able to like run this application so write the application first. If it's running fast enough, then great. If it is not, you profile, and then you see the bottlenecks where they are. And the profiler usually tells you which functions takes the longest to run. And then you take that function and then you start optimizing it. And optimizing it requires you to understand, of course, what is the algorithm complexity, or how the actual code executes. And then you start, let's say, okay, I know why that specific function executes in a slow manner. I know another algorithm that works faster, for example. So you substitute that, right? Or you change your code a little bit. But the main thing here is you always profile. And the second thing is you always should have a budget of some sort. And a budget meaning not the money budget, but for example, in this case, when we are talking about, let's say, about time, you should have a time budget. So for example, game developers, for instance, if we would like to run a game in 30 frames per second, then we have a time budget. We have, I don't know, like how much? Was it what, 16 milliseconds per frame? And you shouldn't run you shouldn't run slower than that, because if I run slower than that, users will actually see some frame cuts. If my budget is 60 frames per second, right now, I have even less milliseconds where I should render a frame. And so the physics, the rendering, these 3D effects, the 3D models, everything has to move according to this milliseconds time budget. Okay, so it is actually super important that you understand this bit. In some places, you're gonna need a budget. For example, say this code cannot execute less in a slower than I don't know how many milliseconds or nanoseconds, right? In some cases, it just you don't have a time budget, but please make it fast enough, and that's it. Make it feel fast, and that's it, without any time budgets. in both cases, we always profile. So that's a super important thing to mention here. You also ask for the space. How much memory space it will consume. And this also an interesting concept. Like, so imagine that you are trying to solve a problem, but the problem is that while you are solving it, all of a sudden you get you consume more RAM than you should, or more RAM than what you have. And right now, your algorithm might be running fast, but you sacrifice the memory, right? So you need to make sure that you are also within the memory budget or the space budget. I think this is also can be obvious, for example, for phones, very much for not only also for phones, but you have also for like embedded systems, like hardware, like for example, Arduinos, Raspberry Pis, embedded systems. What else? Where the memory is actually like constrained, high performance servers, let's say how much customer data you are actually pulling. So imagine, that's why, for example, I think in ERIS-2, ERIS-1 and ERIS-2, one of them, you're gonna learn about pagination, where, for example, if you have 10,000 customers, right now you are in databases, you say select all and filter, right? And then give me, for example, and give me those customers with whatever filter you have. And then suddenly you get 10,000. You will not put 10,000 customers actually in the memory. You will bring the server down to its knees. So because you are not the only one who's pinging, you have 1,000 other users are pinging. Imagine that you are searching through the catalog of Amazon and you say select all where, I don't know, like, and then you start filtering stuff, and then you get 300 items in the 300, let's say not 300, 3,000 items, and which is prepared for you to select from. And then there are other users doing that. And for every user, we load those 3,000 items. Right now, you kill the server. So what we do something which is called pagination, where we, like, you say, okay, I will fetch 10 by 10 by 10 by 10, right? So you have pages of such of like pages of fetching data piece by piece, but not the whole thing. So they can actually control how much space you actually consume per query. So they made an algorithm called, or the data structure called pagination. Actually, you can see this. I don't know if some of you probably browsing Imager or 9gag. It has the same exact thing, but it just doesn't have pages to click, but they do the same fetching. So you can think about these stuff as well. All right, moving along, network bandwidth. So it says in here that how much data will be transferred. Okay, so imagine the following. You are, I mean, you can think about as well the 3,000 thingies, which I can send you all to your computer, the 3,000 elements or the 3,000 products you search over Amazon, and then I send it all to your computer. This is also a bad idea. So every time you search something, I send you like what, 2 megabytes of data. Imagine this happening on your phone, on your 4G or 5G network, and you made 10 queries, all of a sudden you lose from your package, I don't know, like, well, the telecom will charge you, I don't know, like 10 or 15 megabytes. Like you just downloaded because you were just querying things, right? Also, you can think of it as online games. I would like to actually synchronize player positions in a network, and I would like to synchronize it super fast. So I have to use very, very small packets where it says like where the player position is and how to resolve that player position. If somebody shoots a bullet or something like that, how can we resolve it, and so on and so forth. These packets needs to be super tiny in order to be sent over a network really quick, and you get almost kind of real-time responses. Also, network bandwidth, you can think of it as if you are making an AI research. For example, Ilhan was doing an AI research in the classrooms, I think last year or the year before, and he actually was running neural network training over a network of PCs. He had one of the problems where the algorithm was actually quite slow, I think, at a certain point in time, because while he was actually adjusting it because of the bandwidth of the network. So he had a network of machine working together over neural network training. However, the data transfer between the PCs was a bottleneck. So this was also an interesting problem to resolve, right? So that's why one of the algorithm analysis you look at certain things is your network bandwidth. Now, obviously, not all the algorithms work over network, but if you have one, right now it actually is included in the package of analysis, right? Moving along. Power consumption. This is also super important. Your phone is having a variable speed, right? It doesn't execute 100% all the time. Sometimes it sleeps a little bit, right? Will it use the allocated power budget? Okay, so imagine the following: like when you are running a game on your phone, it just sucks out the battery really quick because it actually pushes your hardware a little bit hard. Now, if you don't know yet, once your phone overheats, so if you have actually like a graph, and then let's say you are running a 60 FPS, for example, when your phone overheats, the manufacturers of your phone, they actually have some safety triggers for that. So in order to protect the battery and protect the CPU and the components within the phone, they immediately drop the clock speed of your hardware. So all of a sudden you get a dip, and then suddenly you run at 30 all the time. And then you're constantly hovering around that number until you're cool. I mean, if your phone cools down one day, it will just simply start there, right? Now, obviously, I'm not going to discuss the technicalities behind it and how things go. But one of the things also that it's actually protecting the battery and protecting the power is that they try to not only protect the hardware and protect the battery, but they would also like to reduce a little bit the consumption of your power battery, right? So you don't actually so the phone can last a little bit longer as possible. But for example, dropping the clock speed is mostly protection rather than making the phone last as long as possible. And on the other hand, as a programmer, if you make an application that is not efficient for phones, let's say, it will just suck out the battery super fast, that people will just simply say, whenever I use the application is awesome and cool, but it just simply sucks the battery super fast. And right now, your application became useless for them. So power consumption is super important to look at if you are working with mobile devices specifically, or you made your own hardware, for example, using Arduinos or Raspberry Pis of the world, right? Right now you have something which is called a power budget, which is a completely different story here. In fact, if you are dealing with electronics, or you are an electrical engineer, you're going to have a space budget, but not this. I mean, besides the memory budget, which is the space budget, you're going to have an actual physical space budget. So how much components you can fit in onto a board that it can be small enough and can be usable people right now, for example, complain about bigger phones, right? So imagine that somebody didn't get their space budget right. So they say, okay, that phone has to be of that size in order to be acceptable by the customers. Right now we have a space budget, right? Whatever you're gonna do, you cannot exceed those X millimeters. So your phone has to be, I don't know, like 10 millimeters, or not 10 millimeters, 10 centimeters, sorry, not 10. Okay, so 7 centimeters wide, I don't know, like 15 centimeters tall, and in depth and thickness has to be like what? A centimeter at most, or half a centimeter. So that's the, for example, that's the average phone dimension, I guess. And you play within that budget. Right now you have a space budget. So right now you need to fit in as much components as possible, satisfying the power budget, making sure that nothing overheats. And right now you start doing these interesting balances. And of course, the algorithms for using these stuff or for creating such stuff are, of course, they have their own like study on how to make these kind of circuits and optimize these circuits in order to work in that manner. But I just wanted to mention about the space budget as a physical thing, because it actually exists. Now, the last thing which I would like to mention is regarding the algorithm analysis is the CPU registers, which is actually more like very closely related to embedded systems. So if you are doing embedded system software, doing embedded system, embedded system software, development, software development, would be like here. How many CPU registers? Are you consuming? Okay. Now, kindly note that the algorithm analysis in general are, so let me actually write this in yellow. These analysis are approximations. That doesn't substitute real life benchmarking. You need to benchmark or profiling. Okay? This is super important to understand. Like, for me, I can actually have an educated guess on how bad of a thing can go, and I can take actions. But it does not substitute that. If we start arguing about certain things, like for example, say, hey, this will take actually a very long time to finish. We can argue about certain things that they take a long time to finish, but we need to benchmark it first. Is it actually feasible to spend time and energy and money to actually fix the code or fix something in order to run it faster? And it might not actually be needed to be fixed, right? So it's actually super important to benchmark and profile before you actually do optimization. Premature optimization is the root of all evil. That's the general rule. Okay, so let's actually talk about so now that's actually out of the way, and now we know exactly how we analyze an algorithm. For in this semester, we will be mostly busy or mostly concerned with time, which is the most famous, at least in software engineering or in computer science in general. Also, people are also concerned with space, but for the time being, actually, in order to because the course is more like introductory one, we will be concerned more with time than space. However, for the beginning, we're gonna actually talk about both, but then we will drop out space and focus exclusively on time. Okay. So let's talk about time and space analysis. Now, before I actually go in there are actually a couple of things I need to mention here. Whenever an algorithm is actually written, you write it in something which is called a pseudocode. So when, oh boy, actually you will see it in the books. Nobody actually writes in a programming language specifically. When writing an algorithm, usually we use pseudo code. Okay, and a pseudocode, most of the time, it happens to be a C-style language, most of the time. But let me show you the flavors. In one book, I think the white book, the Introduction to Algorithm and Data Structure Analysis with C, I think, it has, for example, if we have a function called the swap, so swap A and B, you will have something similar to this. So you have temp equals to A, and then A equals to B, and then B equals to temp. It's a simple swap, nothing fancy about it. And then you have the semicolon, obviously, semicolon and semicolon. And this is one representation, which is similar to a C-style language. Now, if you have noticed here, I haven't mentioned any data types, right? I didn't say whether A is a person or an integer or a float or a double, nobody cares. This is how you would swap an element, right? Details of implementation is actually up to you. Moving on next, there is the Pascal side of the world. So this is like the C style. The Pascal style, which you can find it a little bit in the older books, which is begin, and then you have a colon, and then temp. So a colon equals to A, and this means assignment in Pascal, actually. And like when you assign something to something, it's not equality, because equality would be something like this, okay? So this is actually super important to get. A, and when you see that, you shouldn't be like terrified or wondering what this sign means. It just means assignment in Pascal, and that's it. And then you have end. Okay, actually without a colon, I think. So this is the Pascal side, style. In the Introduction to Algorithms and Data Structures, the green book from MIT Press, they write actually the swapping. They would write the swapping something similar to this, swap, but then they indent stuff. So actually, I think they don't even have braces. They say swap space A, comma B, as far as I remember. And then they say assignments go like this. Then and this is how they actually do it, at least in that book, as far as I remember. So you're going to see the assignment goes in that way. So if you see any of the three pseudocodes, you shouldn't be actually surprised. So let's talk about the analysis itself. How can we analyze an algorithm, right? So how do we analyze an algorithm? Right? This is a very good question. So let's actually do the time and space analysis. So I'm actually going to rewrite that swap function again. So I'm going to have this swap A and B. And I usually, like when I describe things, at least I'm used to the C-style languages like C#, C++, and these guys. So you will find me writing this in a C-style language when I write a pseudocode. Temp equals to A equals to B equals to temp. Okay, and then end of the story here. Okay, so let's talk actually about the time analysis right here. So I'm gonna actually talk here about here is the time analysis. Here is the, and let me write it in red, space analysis. Okay. Now for the time analysis, whenever you are actually trying to analyze the execution time of a certain line of code, you'll say it will consume X amount of time units. And we say exactly like time units because a CPU clock speed is variable. And you cannot say exactly whether a CPU is actually running, I don't know, like at 1 megahertz speed or 10 gigahertz speed. You never know, right? So, or 5 gigahertz speed, like this is all speculations. So you say that operation will take a single time unit to run. Whether it's on a faster CPU or a slower CPU, it will actually execute in that single time unit for that speed of that CPU, right? So if you have 1 hertz or 1 megahertz, let's say let it be 1 megahertz per instruction, that means that if I actually see 3 instructions or 4 instructions, that it will, for example, when we say that, oh, sorry, let's actually reduce it to even simpler ones. So 1 hertz per instruction, let's say. So that means that every instruction, like if you have 4 instructions and 1 instruction, you have 1 hertz per instruction, that means you're going to have 4 hertz in order to execute something, to execute 4 instructions. So 1 instruction takes 1 hertz, another instruction takes another hertz, another third instruction takes another hertz, and so on and so forth. So you get 4 instructions, 4 hertz. Okay. So so usually we make an approximation. We say, okay, let's say when we look at temp equals to A, usually assignments, when we look at it in the algorithm analysis, the assignment is actually 1 time unit. So 1, or let me write it here, 1 time unit. And again, I'm not saying microseconds or milliseconds or nanoseconds or whatever that stuff, because CPUs are different. Okay, we should say it takes 1 time unit and that's it. Whether the time unit is a minute or an hour, it really depends, right, on the algorithm and the hardware, obviously. It actually depends on the hardware. So the next thing is, okay, what about this line? And as we already have said that assignments are 1 time units, so this will take 1, and this also will take 1. Okay, that means if this function executes for n times, right? So if I actually execute this function, let's say 100 times, for every time it will just only consume 3 time units, and that's it, right? It's a constant function, right? So f of n, where n is the inputs, like the number of times I'm calling this function, is going to always equal to 3, because every time I call it, it just consumes 3 units and nothing more. Okay? And here we can say, which is a constant time. Okay. Okay, let's talk about the space here. How many variables have we allocated, right? So this is actually a very good question. And when you look at it, you say, okay, I allocated A, I allocated B, and I have allocated temp. Each one of those, when we calculate the size, in the old books or in the books in general, we usually don't say in megabytes or bytes, we say in words. So this, it took one word. This one took one word. This took one word. Okay. Do you remember the word definition from Introduction to Information Technologies? I think 2 bytes is one word, as far as I remember. As far as I remember. So yeah. So the space analysis, S of n. So whenever I actually run this function 1,000 times, for every time I will have to allocate 3 words, 3 bytes, 3 megabytes, 3 gigabytes, it doesn't matter. Whenever I actually run this function as many times as it can get, every time it runs, it will consume exactly this number and it will never grow, right? It will never become bigger. And this is why this is also a constant time, or sorry, it takes a constant space. So in order for this algorithm of swapping to function, because this is an actual this is one of the simplest algorithms you can think of, swap to variables. So in order for this algorithm to function, the minimum requirements for it is, for example, 3 words, which is, let's say, 2 bytes per word. That means that you need 2 times 3, which is 6. So you need at least 6 bytes in the memory to be there, reserved. Nobody touches them in order for this algorithm to execute properly, right? And you need your CPU to be fast enough to do these stuff in, to do these 3 instructions per hertz, for instance. So right now it will take 3 hertz in order for it to execute, right? Does this make any sense?
Yes, it does.
Okay.
Yes.
Anybody has any questions regarding this? This is super important to get correctly here. If you actually don't have any further questions, let us talk about some other things as well. One of the things which you have to understand is that we do approximations. Okay. In our code, like when we do algorithm analysis, we always do an approximation. It's not something that's hardcore, super precise, exact. Okay. So for example, right now we said that the complexity or the time analysis of this guy is 3. Usually we usually ignore these constants. In the future, you will see that, well, I'm just simply gonna say, okay, it's 3. I will just consider it as 1. Because we are approximating things. We are busy with, in asymptotic notations, calculations, we are busy with the big stuff, not the tiny stuff, right? Because the tiny stuff are irrelevant. They are not, they are not useful. I need the heavy stuff, the stuff which will hit me like a truck. So let's say if we consider and I've given this example in the class, x equals to a times 5 plus b times 6. Can somebody tell me how many instructions there are in there?
Three, I think.
Can you please describe why? I'm not saying that you are wrong, but I think you are missing one more. But let's actually, let me listen to the reasoning.
I'm thinking there's a times 5, b times 6, and a plus
and the
B.
result, yeah, and the result is the result of that addition, right? So
Yes,
this,
yes.
this, and this, right? You are missing one
Yes,
more.
yes, yes.
Which is this
Ah,
assignment,
yeah, yeah.
right? So
Yes, yes.
here, this is actually breaks down to 4 instructions. Or let me actually write this in text. Breaks down into 4 instructions. Ah, I'm writing it badly, so badly. Instructions. But good job, good job. So when we say it breaks down to 4 instructions, I will not say that the time complexity of this guy is 4. Okay, we will not say that. We approximate the statement and say it takes 1 time unit. Again, we are just approximating here, nothing more. Okay? Because this is actually will execute all the time in exactly the same time. It will always take the 4 instructions, and these 4 instructions will execute per CPU cycle, which is almost always constant because you have the crystal clock is beating at the same time every single time, right? So we consider it like just a constant. Like do not make a fuss about like 4 hertz or 5 hertz or something like that, because it will just execute one time. Like not four, I mean, it will break down into 4 instructions, but we don't need to worry too much about it being just running at the same time all the time. So this is actually super important that you get that. So whenever you look at the complicated algorithm, and then you say, like you see like a bunch of lines here, a for loop somewhere there, and then all of a sudden you get a bunch of assignments. Let's say here bx equal to cx and so on and so forth. You just simply say, oh, this is actually 1, and you completely ignore, right? And then you are busy just with the for loops and the while loops and the if statements, because these are the branches. Because when you have a branching, you say, the best case scenario is this, the worst case scenario is that, because you need to test both branches and see what will happen if it was false or true, and so on and so forth. But we're going to get into that later. So now that's actually out of the way. There's a super important thing to mention here, is that we are always calculating, or when we say calculate, like when we write the algorithm analysis, which everybody gets wrong, unfortunately, is that we look in algorithm analysis, and I will reiterate that later because I know that you're going to forget this. In algorithm analysis, we observe, or we describe the complexity in terms of polynomial order. Okay? Meaning that when I actually look at this is right now will take execution time O of 1, where O is called the polynomial order. Everybody on the internet will say big O, right? Oh, sorry, this is O of 3. sorry, not n. It's going to be O of 3. Apologies. Okay. Everybody will say literally big O, and it is not big O. And we're going to study what a big O and what a big theta and what big omega are. This is not big O. This is called the polynomial order. The asymptotic notations are the categories of these functions. Okay, and we will study again, we will mention them again when we get there. So when you see an O, you say it's a polynomial order. If somebody asks you what is the asymptotic notation, then you immediately categorize whether it's a big O, big theta, and big omega. And this is the problem, because this is why it's confusing a lot of people, because we use the big O for the polynomial order. Okay, so this is where the O coming from. Okay, and the big O, which is the actual notation, and everybody just gets confused about it. So and I've actually explained it to many people before on the internet, even when we had the chats in the game developers kind of Discord channels. I had to describe it to many people why it is O as a polynomial order. It's not the actual asymptotic notation. Before I actually let you go, I will actually show you a method here, which we call the frequency count method. And we will reiterate that again next week. So I'm going to bring it up next week, and then we're going to analyze it again. So I refresh your memory. So let's say that you are summing up. So let me actually write this down. And I'm going to actually again mention it again. Don't worry. So frequency. But it's important to get your brains working now about it. Frequency count method. Okay. Now, please remember how we broke this guy down, right? So this is super important. Imagine that you are having a sum, and I'm just going to actually write it here down in the middle, because I would like to analyze the space and time complexity. And then soon enough, we will actually stop analyzing the space. So you have an array of an input, array of numbers, okay? And you have n. How many numbers do you have in that array, okay? So in that sum, I'll just simply say s equals to 0. And I would like to sum all the numbers in that array. So if I have 10 ones in the array, I would like to get a result of 10, okay? For I equals to 0, I is less than n, I plus plus. And then right here, this is something what you would write in C++ or C#, s plus a of I, okay? And then here we're gonna return s, which is my sum, right? And again, as you can see here, I didn't actually specify any types. It's just pure code, right? Nobody cares about the types here. Right now, you can make this doubles, floats, persons, whatever, okay? Now, let's talk about the time complexity here. And I will actually put the time here. So time analysis. Can somebody tell me what is the cost of this guy?
It's 1 probably.
Okay, good. Now let's discuss the cost of the 4. Can somebody tell me what is the cost of 4? Let's actually break it down, obviously, because you cannot actually, because this line of code is actually broken into multiple pieces as similar to here, but not exactly the same, obviously. So how much time does this run?
1.
1. Okay. How much time does this run?
Also 1.
Nope, it cannot be.
It's not?
Because this check is happening every time you loop, isn't it?
Yes,
So-
it's n times.
Yeah. So it's actually, no, but it's still not n times, it's even more. It's actually n plus 1. Because this guy has to fail in order for you to exit. Otherwise, if it doesn't fail, then you will not exit, right? So that's why, like, you have, if I is less than, so if I is 10 and n is 10, then it will actually fail because 10 is not less than 10, right? But if I is less than 9, it will actually still work. And if you are counting from 0 to 9 is actually 10 times, right? And if you are actually starting from 0 here. And then you need plus 1, which is making I equals to 10. And then when you have 10 less than n, which is equal to 10, let's say, then you are actually running this check n plus 1 time. This guy run n times, however. That means that you have how much of that stuff right now? 2n plus 2. This is the execution time for that loop, for that side. Now the question comes here is, how many times does this actually execute? Okay. Nope,
Maybe
it can
times.
exactly, it executes actually n times, exactly, not 1, but n times. How many times does this execute?
Only one.
Only once, exactly. So if I actually sum all this up, that means that I have, like, how many of that stuff right now? 3n plus 4, right? If I sum all these guys up, hopefully I didn't miss anybody. And if I actually get 3n plus 4, we usually approximate this. So this is approximated to a polynomial order O of n. And this is the order, not a big O of n. It's called the polynomial order n. And the polynomial order, you pick it up because of the highest, the number with the highest exponent, right? All these guys with the exponent of 0 except for this guy, and this guy has the highest exponent. And if you see, I ignored even the 3 because we don't care that much about it. We care with the highest exponent, so we actually just simply took n as is. Okay. Because I know that I exceeded my time here, but let's actually, like, really quick. Can somebody tell me about the space? This one is much easier now. How big is A?
N words.
Exactly. So N. How big is S?
1 word.
1. How big is, how much do we have? We have, how big is N? This guy.
1 word.
Also 1, exactly. How big is I?
1 word.
Exactly. So it's actually n plus 3, right? So it takes a space approximately of a polynomial order of n, right? We just simply ignored the 3 here. Hopefully I didn't forget anybody. S-I-N. Yeah, I think this is it. Okay. Does this make any sense?
It does.
Okay, in any case, don't worry about this. I'm gonna actually recover this example again to refresh your memory before we dig deep and then analyze more algorithms in that way. Algorithm analysis is super important, and it's super important that when you look at a code, you immediately know how much it will cost to work with. All right. With that being said, let me actually just Stop recording.